Okay, Assalamualaikum warahmatullahi wabarakatuh. Good evening, everyone. Can you all see my slide?
Yes, Doctor, again.
Okay, all right. So, just before I start, I just want to wish everyone Selamat Hari Raya, Aidilfitri, Maaf Zahir Batin to everyone. And also hope you all had a good holiday or week at least. Okay, so let's move on to our next chapter, chapter 7. This is a very short chapter, so we'll probably finish in half an hour or so. But then we'll definitely continue on chapter 8 next week. So today's session will be very short, just a brief one on fluid motion. So let me just start with this one. So under fluid motion,
Doctor, think you muted yourself.
sorry, thank you for letting me know. Okay, the fluid motion is all about of how the air fuel mixture enters the combustion chamber and how does it behave under compression in the intake stroke. So this is all about the fluid motion. Okay. So combustion chamber and air movement. So combustion chamber is a definite closed space formed by three separate engine parts. So if you can imagine, if you're in the combustion chamber, the environment is being enclosed by three main parts, which is the cylinder head, and then you have the cylinder wall, okay, which is the cylinder block, okay, and also the piston top surface. Okay, so you have three main components, which represents the envelope of the combustion chamber. So such closed space, when subjected to pressure rise during the compression stroke and change in volume, forces the gases within it to move in various kinds of motions. Okay, and because the piston moves from TDC and BDC, it it compresses the air inside the combustion chamber, which in turn moves the mixture into a motion. Okay. So there's basically five types of motion in a typical combustion chamber, but the main ones are there's only four main ones. We're gonna touch on each of the motions. So efficient operation of engine depends on the level of mixing process between the air and fuel. Give me a second. Sorry. So such mixing process is enhanced by various motions of both fluids during the intake and compression stroke, and so enhances the proper operation of the engine. So these motions can be summarized as follows. It can be turbulence, it can be swirl, it can be squish, it can be tumble, and it can be frivix. It depends. Some engines are actually designed for turbulence. Some engines are designed for swirl, whereas and also some other engines also are being designed for squish, tumble, and so forth. So you can't really. It's pretty much. It's very difficult to have different motions at in one engine. They are usually designed to for certain they are actually designed for certain motions. Okay, depends. if the engine is a performance engine, probably it is designed for turbulence, for example. Okay, if the engine is designed for fuel economy, then the engine is designed to have a swirl or squish motions and so forth. Same goes to tumble and crevices. So this type of motion is created by the piston action from of whereby the piston moves from BDC to the TDC, especially during the compression stroke. Okay. However, due to high velocities involved, all flows of air into and out and within engine cylinders are turbulence flow. Hold on. Okay, sorry. So, however, due to high velocities involved, all flows into and out of the combustion chamber are within the engine cylinders are turbulence flow. Okay, this is only applicable if there is a high velocity. Okay, so during turbulence flow, all flowing particles experience random motion fluctuation in all direction. It is like haywire. Okay, because of the high velocity of the air mixture entering the combustion chamber. There are advantages of turbulence motion. Okay, it distributes the fuel. Okay, it helps, it assists the mixture between air and also fuel. Okay, it helps the fuel to evaporate even more effectively. Okay, it assists the combustion because the fact that you have a proper mixture between fuel and air, and also it reduces afterburn. So in other words, if you have a proper mixture between air and fuel, then you definitely reduce the afterburn. Okay. Whereas on swirl motion, okay, it is a rotational circular motion of gases, okay, imparted during suction stroke. So swirl motion is usually happens during the intake stroke. This is when the valve starts to open. Okay. It can be generated by designing intake system components to allow tangentially entry of gases. So you can have the swirl motion by designing the air intake system, okay, the intake ports, the angle of the intake valves, and so forth, to create this swirl motion. Okay, so the advantages of swirl motion may be summarized as to enhance the mixing of air and fuel, giving homogeneous mixture, and speed up the spreading of the flame front. Okay, so those are some of the advantages of swirl motion. So if you can imagine the swirl, you can see the picture over there. So uh, if you compare the arrow, if you look at the top left figure, that's a comparison between the difference between a non-swirl on the left and on the right is a swirl motion. So what it does is basically designing so that the airflow has some restriction to create that swirl motion. Okay, this is by using a small valve in the intake port. Okay, some engines are actually being designed instead of using valve. They could what they did was to have a different length of the intake runners so that you have a different speed between the two channels, okay, between the two ports. This is for the main purpose of having that swirl motion inside the combustion chamber and so forth. Of course, there's many methods. Other methods, of course, by using the intake valves. Okay, just imagine if you have two intake valves. Okay, if you could open one of the intake valves slightly more earlier than the other one, then definitely we can create a swirl. Okay, so that's one of the reason why they would prefer to have a actuator valve system instead of camshaft system, so that you can actually manipulate the opening of the valves. Okay, so that is swirl. Okay, so it is a eccentric induction process. Okay, air entering engine cylinder from tangentially direction. Okay, air contoured intake runner, air contoured intake valve, and so on. So, of course, there's so many reasons, but overall, the main aim for the design of those engines to get the swirl motion is to have the air in to enter the combustion chamber in a tangential direction. Okay. Yeah. So if you look at the figure B over here, that is the top view of where you can see the swirl motion of the air. Okay. So how do you actually determine the swirl? It is a ratio is being used, and it is called a swirl ratio. So a swirl ratio can be defined as a dimensionless parameter used to quantify the rotational motion within the cylinder. So you can actually calculate how you can actually measure or quantify the swirl by using the swirl ratio. Okay, so usually swirl ratios are being measured by a special device, and that would represent the measurement would represent the swirl ratio, which is a product of the angular speed divided by the engine speed, or the swirl tangential speed divided by the average piston speed. Okay. One simple way of modeling cylinder swirl is by using paddle wheel model. So paddle wheel is one of the common standard measurement tool which is used to measure the swirl ratio. Okay. So the volume within the cylinder is idealized to contain an imaginary paddle wheel that has no mass. So as the paddle wheel turns, the gas between the blades turns with it, resulting in a cylinder of gas or rotating at velocity. Okay. So the mass motion of inertia of this cylinder is calculated by the mass of gas mixture in the cylinder times the bore square divided by the uh, 8. Okay. So whereas the angular momentum is the inertia times the solid body angular velocity. So those two are some of the fundamentals of calculating the swirl motion. Whereas there are other types of motion besides swirl. Of course, you have the squish. Okay, it is a radial motion towards the center line of the cylinder. So just imagine if you try to squeeze everything, squeeze all the air towards the center of the piston. That is what they call a squish. Tumble is a rotational motion around a circumferential axis. So it is the opposite side of swirl. So because on the swirl, you have the tangential direction, whereas on the tumble, it is a circumferential axis, based on the circumferential axis. Crevice motion is flow into the very small crevices of the combustion chamber. So these are some crevice motion is mainly the motion of where the air tries to go in between gaps or between crevices inside the combustion chamber. For example, in between the piston and also cylinder wall, in the piston rings, and so forth. Okay. The squish motion, okay, this is basically a squish and reverse squish is a radial motion towards the center line of the cylinder generated by recess located at either piston or the cylinder head. This is basically quite very common in a direct injection engine, whereby in direct injection engine they are trying to focus to increase the density of the air towards the center of the combustion chamber. Okay, this can only be done by having a special piston or a dedicated piston with usually with a bowl in the middle of the top surface. Squish motion occurs only during compression stroke. Okay, so reverse squish motion occurs in the expansion stroke. Okay, so due to very small clearance volume when the piston approaches TDC, this is during the compression stroke, the radial flow of air from the periphery to the recess is produced. This is squish, or in other words, it's trying to squeeze all the air towards one point, okay, or one area. So during expansion, this is when the volume starts to expand, the piston starts to move from TDC to TDC. The burning of the gases are forced outward. Okay, this is the reverse of squish. Okay, so you have the normal squish and also the reverse squish. Different differences. It happens in a different event. Squish happens during the compression stroke, whereas on reverse squish happens during the power stroke. And then you have the tumble motion. Okay, this is what I said, that it's like the other way of the swirl motion. Okay, it is actually a rotational motion, but it is in fact generated by the squish motion around a circumferential axis. So therefore, tumble caused by squish as piston approaches TDC is a motion about a circumferential axis near the edge of the clearance volume in the piston bowl or the cylinder head. So you can actually see that is how it is being described, okay, of how air does actually tumbles caused by the shape of the piston bowl. It has become one of the important parameters in enhancing air fuel mixture for modern engine, especially in gasoline direct injection engines. Okay, so like the swirl ratio, tumble can also be measured and quantified. It is a dimensionless parameter, doesn't have any units, it's because it is just a ratio to characterize the magnitude of the tumble. And of course, you can actually calculate the tumble ratio by dividing the angular speed of tumble with the engine speed. So you could see difference, as you can see, of how is there is basically illustration of how the air is being tumbled. Okay, it is being caused by the most of the time caused by the shape of the piston bowl. Okay, and of course you have the Krivix motion. Like I said, this is the small miniature motions of air mixture that goes in between gaps and crevices within the combustion chamber, or very small volume, such as the clearance between the piston and also cylinder wall, and also there's a gap in the gaskets between the cylinder head and cylinder block, and around corners and edges, especially in between the piston rings. So that is pretty much on the fluid motion. Nothing much on this fluid motion. Just to summarize everything back. So under the fluid motion, you need to understand there's 5 types of motions. We have turbulence, swirl, squish, tumble, crevices. You should be able to describe and illustrate these motions. On top of that, you should be able to calculate the swirl ratio and also the tumble ratio. Okay, so there's the formula to calculate the swirl and also tumble ratios are quite straightforward. Okay, so there's nothing much about that. It is a very short chapter on this one. So, do you have any questions?
No, sir, no.
Yep. Okay, thank you very much. I think this is a very short
Sir,
chapter. Yes, Ken.
just one question. It's
Yep.
about crevice motion. Is
Yeah.
is crevice motion something that we want, or is it something bad? Because to me, it seems like there shouldn't be any mixture going into the space between the cylinder walls and the cylinder.
Yes, that's a very good question, Imam. As much as possible, they want to avoid crevices motion as much as possible, because it may affect the main motion that is designed for the engine. For example, if your engine are designed for swirl ratio, so as much as possible, you want to avoid crevice motion, because it might affect the main motion, which is swirl. But nevertheless, you can't actually avoid you cannot eliminate crevice motion totally. So what you can do is try to minimize, which is why the engine manufacturers engines are actually designed to have a very smooth curves, very tight clearances, but not to the extent of it creates a friction. But nevertheless, it depends. This is what actually determines. This is one of the small areas of determining whether engine are actually a good design or not. Is that okay, Imam?
Okay, thank you.
Yep. Okay. Okay. Just to summarize everything back, just to remind you, this chapter is very straightforward. You need to know those five motions. You should be able to describe those motions, and you should be able to use the swirl ratio and also tumble ratios equations. Straightforward. Is that okay? Okay. Next week we will move on into combustion chamber. Combustion chamber. Sorry, combustion chapter. Now, combustion chapter is a pretty quite important chapter. We're gonna explore and understand about the combustion process itself, the combustion itself. Okay. So that we will start next week. But as for now, today's today's session will be very short. Nothing much. So if you don't have any questions, if you do have questions, please do email me. But other than that, I'll see you next week. Thank you very much, everyone. Eid Mubarak.
Okay,
Yes, Daniel.
sorry. Um, about the presentation for next week.
Yes.
Uh, I think I
I
have
will.
given those who have already presented. So yeah,
Sorry, Daniel. Can you?
I've already sent you the list of names that have already
Yes.
presented. Yeah.
Yep.
So
I will. Can I give you the list later to you through
okay.
Daniel?
All
Is
right.
that okay?
Yeah. Okay.
Because I haven't got the time. Sibuk beraya kan. Haven't got the time to like identify those yang belum present for the 5 minute.
Yes. Yeah, that's sure.
But I'll give you the names later today
All
via
right.
Daniel.
Okay. Then I'll pass down to the group.
Yep. Okay. Other than that, I think yes. Okay. Can.
Do we have attendance?
Sorry.
Do we have attendance?
Yes. I just post in the chat.
Oh, okay. All right.
Thank you for reminding,
Okay, I see the chat.
Fahim. Thank you for reminding. So those please